Uh, All right, good morning, everybody. I'm going to get started as people continue to trickle in. Welcome. We have a lot to cover today, so I want to make sure we have as much time as possible, especially to get to the demo, which I'm sure most people are going to be the most interested in. So welcome. My name is Kathleen Fallon. I am a coastal processes and hazards specialist with New York Sea Grant. I'm joined today by Dr. Lee Herdman and Dr. Robin Glass from the USGS New York Water Science Center, who are going to talk about the compound flood hazard assessment study that they completed. And then we are going to have Jason Finkelstein, also from the Water Science Center, New York Water Science Center, walk us through a demo of the compound flood hazard mapper that was a result of the study. Um, oops. Um, I will mention that this study was conducted by USGS with funding from the Long Island Sound Partnership. Um, Again, this is the information for who would be presenting today. I have contact information at the end of the webinar that I will share with you guys. And throughout today's our webinar, we're going to spend a few minutes talking about the project, how it came about, what its goals were. Then again, like I mentioned, USGS will talk about the actual study. And then we'll spend the majority of time going over a demo of the new mapper. I will mention we have a lot of people register for this webinar and a lot of information to go through. So we really are not going to have time for live Q&A sessions. So I have this QR code here, and we will be putting the link in the chat but to a Qualtrics form where you can submit all of your feedback, input, thoughts, ideas, comments about the mapper, as well as any questions that you have. And we really encourage you to utilize this format today, because we will be answering all of the questions, compiling them into a document, and we will be sending that back out after the webinar. So those questions will be answered. We're just going to try and limit that time today so that we really can go through in great detail all of the information. So with that, I will dive into a quick discussion and overview. As I mentioned, this project started in 2021 with funding from the Long Island Sound Partnership, and USGS studied the multiple flood drivers and their co-occurrence. They assessed the flood drivers and how their co-occurrence. And then in 2025, we launched the compound flood hazard mapper right at the end of 2025. So this is still a very, very new tool, only been out for a few months now. So what we've been doing since the launch of the mapper is going out, providing outreach. Some of you may have attended some of the in-person workshops that we held throughout the Long Island Sound region over the last couple of months. And New York Sea Grant's goal in presenting and hosting these outreach opportunities is to gain feedback on the tool from the people who will be using it, and their input. And we're compiling that information into sort of an assessment of the mapper of the tool that will hopefully be able to inform USGS. And as you might hear throughout today, through some of those workshops, we've already heard feedback that has been leading to different improvements and changes in the mapper. And I'll just mention quickly that with your feedback and input, we will be developing a toolkit for people who are not able to attend workshops, or once workshops have been completed, they can still get that valuable information to learn how to use the mapper in their work. So as I mentioned, the mapper talks about different flood hazards. The main three that are included in the mapper are precipitation, which is when stormwater runoff occurs as precipitation runs over land surface. It covers groundwater, which groundwater flooding, which occurs as the water table rises above the ground surface, and then of course it covers third coastal flooding, which is what what we really focus on, what we see very often in the Long Island Sound watershed. Which is when low-lying land is submerged by seawater, whether it be during highest high tides, storm surge, or as a result of sea level rise. So I want to differentiate here that there is a flood hazard and then there's a flood risk. So when we talk about flood hazards, that is the potential for flooding to occur versus a flood risk, which is the probability that that flood hazard will interact with society. And we care about this because communities are forced to consider how they react, plan, and manage coastal infrastructure and investments. And as people are faced with this risk and hazard, they have to consider adaptation strategies. And adaptation is when the communities are taking actions when they're faced with the flooding. And in this graphic here, you can see a smattering of different options that exist for communities, such as relocation or participating in buyout programs, considering implementing nature-based features, planning through comprehensive resilience plans and disaster recovery strategies, conserving floodplain areas. So these are all different things that actions that communities can take, but without the science and the information to back those actions or strategies, it would be hard to determine what is the most appropriate. So I definitely want to take a moment to acknowledge that there are currently existing tools. This is not a brand new mapper that is the first of its kind. We know that there's such tools on the federal level, such as the Coastal Flood Exposure Mapper, the FEMA flood maps, on the local level, such as the New York City stormwater flood maps. And I'm sure there's I know that there are plenty others that you on the call probably use in your daily planning and different flood related activities that you're working on. But what is unique about this new mapper is that it focuses on compound flooding, which is when two or more of these flood drivers are occurring together, resulting in impacts being compounded. So, for example, in this image, you can see that you have some rainwater happening with runoff, with infiltration from high tide, plus a storm surge, and all these things, and groundwater, all these things happening together. And that is the goal of this mapper, is to combine those flood drivers. So very quickly, like I mentioned already, you have four components of this mapper. You have a mapper that shows the rainfall flood hazard score, the coastal flood hazard score, and the groundwater emergence flood hazard score, each as separate mappers, but then come together and show the co-occurrence of the compounding flood hazard scores. And I will mention just very quickly to remember as I turn it over to USGS, they're going to talk a lot about the flood annual exceedance probability, which is this concept of the 100-year flood. And a reminder that a 100-year flood does not mean that it happens once and then not again for 100 years, but it's rather it has a 1% chance of happening any year. So with that, I'm going to turn it over to Liev and Robin from USGS to talk about the study that they conducted to look at the co-occurrence of all of these flood drivers. And I will mention again after that Jason will be talking about the mapper, which is focused on the Long Island, New York City, Westchester area, and coastal areas of southern Connecticut, and that it displays a susceptibility to coastal flooding, flash flooding, groundwater flooding, and the co-occurrence of all of these three flood drivers. and a lot of great supplemental maps that Jason will be sharing with you. And again, to reiterate, the goal of this mapper is that it will be a tool that helps communities understand the areas that may be vulnerable to compound flooding. So with that, I'll turn it over to Liv.
Yeah, hi everyone. My name is Liv Herdman, and I work at the USGS, the New York Water Science Center, and was the technical lead of this project. And so I just want to say that the this compound flood mapper is a living tool. We're hoping to continuously update it. And as long as we keep getting funding to do so, we want to incorporate new data sets and make it as useful as possible. And to that end, since we've created these slides, we've done some outreach and already made some changes. So when Jason does do the demo later, it might not look exactly like what you see here, but it's not shockingly different. So don't be alarmed when it's different. But now I'll just walk you through briefly, very briefly, the analysis that was done to kind of arrive at these hazard ranks on the whole study area, which you can see here. It comprises all the watersheds that drain to Long Island Sound, in addition to the southern part of Long Island. Was divided into a 900-meter grid. And so each 900-meter cell has a hazard ranking for all of the components: groundwater, rainfall, coastal, and compound. So this is the groundwater hazard analysis. So this is showing the depth to water over the study area, or the depth of water. And so the hazard was calculated based on how shallow that is. So when the depth of groundwater was below 6 feet from the surface, which is a depth that could be impacting your basement or other infrastructure, it has a higher ranking. And then it's also ranked even higher when it has a particular type of soil group, which reflects the permeability of the soil. And then the lower rankings have a larger depth of water, so it's below 6 feet, and 0 and 1 have greater than 15 feet depth to water. And then the next slide talks about the rainfall hazard. So we can go to that one, I think. And this was determined based on many different layers of information. We want to analyze the land surface. So here we see the curve number, which is a empirical number that represents kind of the amount of runoff that happens during a rainfall event. So high numbers mean there's a lot of runoff and no infiltration. And so the really yellow areas correspond to high curve numbers, which are also usually densely developed areas because there's a lot less permeable surface when you have pavement. The next runoff layer the next land surface layer that we analyzed was drainage density. So we looked at how many drainage channels, we did an analysis of the digital elevation model to look at the density of drainage channels. The next layer that we looked at was another analysis of the DEM, but to look at the slope of the land surface. And we also analyzed the digital elevation model to compute a ponding percentage, which is basically how much we analyzed where there were local closed depressions in the topography, so a place where the water could not drain out, and then computed the percent of the land area that had a closed depression. And then we also analyzed the rainfall frequencies and durations over the study area. So this is an example of the 1 hour 100-year rainfall event. We took all of these land surface areas and put them into a model to try to predict where flood, we use multi-criteria decision making to predict where floods would occur, and we compared it to storm events. I think that's shown on the next slide. We looked at the storm events reported in NOAA's database. So all the storm events reported are shown there, and when we looked at what the most important variables were for predicting rainfall hazard, we found that curve number was by far the most important prediction number, and next was ponding percentage, and then the 1 hour rainfall intensity, and then the drainage density. So yeah, so and this is showing kind of the weight of each of those factors on the left side. So you can see here that, yeah, that's the order. Curve number is by far the most important. So basically, which is makes sense, right? That if you have a high curve number, you don't have any infiltration. If you have a high ponding percentage, you have a lot of places where that water can pool. So basically, it's showing that where the water has nowhere to go, it's going to cause flooding, right? Because it's stuck in these little ponds in places where there's low infiltration. Yeah, no, we're done. We can move on. So yeah, so then, and then the final thing we do is coastal hazard analysis. And I just want to say, I realize this is a bit of a whirlwind background, but the goal is to get you guys actually interacting with the data that we are showing on the mapper. So please, yeah, follow up with questions in the link that Kathleen shared, and also feel free to reach out later if you are looking at the mapper and have questions. So the coastal hazard analysis, what we did was we took all the observations of water levels. We also looked at waves at the blue stations. Water levels are from the red stations. And it's showing here an example of the analysis we did at the battery, where we took the time period and calculated the storm surge. So that's shown, the time series of storm surge available at the battery is shown in that bottom panel. And then we looked at the extreme values of storm surge. You can see Hurricane Sandy is the biggest value in that time series right there in 2012. And then we fit an extreme value distribution to those values. So that we could look at when the 100-year, 10-year, 1 year, the different return period storms from that extreme value. You can see that there's a lot of uncertainty when you get to the 100-year storm, but we are able to then take those water levels and their associated return periods or frequencies of occurrence and project them using a smart bathtub algorithm to see how much flooding actually occurs on the land surface, and then create a ranking based on that, the extent of the area that was inundated. And now I will pass it off to Robin, who did the copula analysis.
Hi, everyone. Robin Glass, New York Water Science Center in Troy. And so Leif just went through the groundwater, the rainfall, and the coastal hazard analyses. Essentially, where's the water going to go in each of those hazards alone or independently? But how do you combine them all together to look at how they might actually happen at the same time? So this compound ranking score is really a timing score. So we're looking at over the historical record over the last 52 years, we're looking at how often the most extreme events happened at the same time. So we're talking about groundwater near to the surface, we're talking about high storm surge, and we're talking about heavy rainfall kind of all happening at once. So this is really a timing score, and the map here just shows you the stations that were used. I didn't show the groundwater stations because there are so many of them, but these are the rain and coastal stations used over a long time period. Go ahead and switch. There we go. So if we look at just precipitation and surge, and by their dates, we plot them together, we can kind of see how extreme they are by kind of drawing a line at, say, the 99th percentile of the whole past half century. And that's what these lines are on this plot. So if you look at the x-axis or the horizontal axis, it says precipitation. Now we drew a vertical line here at, say, the 99th or 95th percentile of precipitation. And everything above that can be considered extreme. Likewise, when you look at the vertical axis for surge, there's a horizontal line. Everything on top of that horizontal line would be an extreme surge event. And when they're both extreme, it would be in the upper right-hand box. So you see how we can start to visualize these historical records and how they happened together. So in this case, Sandy was actually an extreme surge event, but it wasn't an extreme rain event, whereas Irene wasn't as extreme as Sandy and surge, for example, at this specific station, but it was extreme in rainfall, and it actually happened to be extreme in both. So that's just kind of how we're wrapping our heads around the compound flood score. Next slide. One interesting finding that we found is if we're looking at the extreme rain events in orange in the top histogram, we can kind of see by month. You can see January, February, March. That's what those abbreviations are on that horizontal axis. You can kind of see that bump right around August, September, October. And that bump means that there were more heavy rainfall events during those months. And this is for all of our stations binned together. And then in the bottom, in the blue plot, you can kind of see where that bump was in the rain. It's like empty, right? So it's like this U shape. So we're actually seeing a lot fewer events in May, June, July, August, September for storm surge. So you can see there's like this mismatch in timing. We see the most extreme surge in the winter, and we see extreme rain all year round, but it kind of gets bumped up in either it's like July, August, September. And this is most likely due to localized convective rain events, just because if this was all because of hurricanes, we'd probably also see surge at that time as well. So it's just a really interesting timing piece for you to consider as well, that when we're talking about the orange and the blue happening together, we're really talking about the winter months. Now, it just so happens on Long Island and Southern Connecticut, the groundwater is highest in the winter months as well, for separate reasons, right? This is the cold season. This is when the aquifers are most full. This is when there's least amount of evaporation. So we start thinking about these three things happening at the same time, and it's turning out to be kind of a cold season story. And the types of storms that occur in the cold season happen to be more like nor'easters rather than hurricanes and convective events, which is just a really interesting timing piece. Next slide. So we put all of this timing together and we kind of plotted how often. So in one part of the region versus another, you might see these things happening at the same time, whereas in other parts of the study area, we don't tend to see them happening at the same time. And so that's what the compound score is. And these are the same orange and blue colors. So in the top plot, you can see like we tend to see the rainfall. This is when we're just looking at the heavy rainfall, and then we look at the corresponding surge, whereas in the bottom plot, we're looking at the heavy surge and corresponding rain. So you can see there's a lot more blue dots than orange dots, and that means that during the high surge events, those tend to be more compound. They tend to be more than one thing happening at once. Rather than the orange dots, which are much fewer. That means if you have heavy rain, it's usually an isolated rain event that is not accompanied by surge. Next slide. So putting this all together, what you'll see in the mapper today, you're not going to see the dot maps. Those are really just kind of the mathematics that went into the result. But what you're going to see is this plot A here on the left. It's going to look a little different because we did update it with some new data. But you're going to see colors from yellow down to dark red. I'm not sure what Jason's color scheme was on the map, but at least here what you're looking at is in red, we tend to see all three things happening at once more often, whereas the yellow and lighter colors, they'll still be happening. You still get floods. We're not saying in Port Jeff, for example, that it never floods. What we're saying is the most extreme rain isn't necessarily happening at the same time as the most extreme high groundwater and the most extreme surge, all kind of within a few days of each other. So that's what the compound hazard score is. I want you to think about timing and co-occurrence, and not saying, oh, this region doesn't flood and this region does flood. Instead, we're looking at how likely are these things all to happen at once, especially in the extreme end. So we're talking about 100-year, 200-year storms, those really big ones. Are you to expect those to happen at the same time? And we can kind of see the geographic distribution. And in the updated map on the mapper that Jay's going to go over, you can see like Suffolk County is really lightly colored, whereas Nassau County has like a lot darker colors, and also Western Connecticut versus Eastern Connecticut. And that's really interesting because if you think about the land cover in Suffolk County versus Nassau County is a lot more paved, it's a lot more impervious, it's a lot more densely populated. So when it does rain, they have a lot fewer kind of protections in place, whereas over in Suffolk County, we've got the Pine Barrens, we've got agricultural land, we've got parks that are kind of absorbing that rainfall. So that's just something to keep in mind, that this is a timing score. Next slide.
There
That's it. Yeah. So you might see when you're clicking around in the mapper that the compound hazard flood score is like a 5, but then maybe the rainfall is a 1 or a 2. And just remember that if it's a 5, even if the 3 are low, let's say it only gets a trickle of rain. Let's say you're in the desert and it hardly gets any rain every year. We're still looking at that kind of 99th percentile for that dry area. The groundwater and coastal flooding, they might be kind of small in themselves, but remembering that the gray triangle in the middle, the compound hazard score, regardless of how big they are, is the timing score. So how likely is it that those 3 things are going to happen at once, whether they tend to have small magnitudes or not? So just remember, the middle one's timing, and the other 3 aren't necessary. Those are more like water levels type of score.
Great. Thank you, Lieve, and thank you, Robin, for that great explanation and going over through your study. So now I'm going to turn it over to Jason, who's going to do a live demo and walk us through the mapper. I do have the link here. If you have a second screen or a tablet you want to follow along with. And again, I will be dropping a link in the chat, and here's the QR code. Remember to use, and you feel free to submit as much feedback and as many questions as you want. So with that, I'll stop sharing, and Jason, you can take over.
Okay, thank you, Kathleen. Thanks, Robin, and thanks, Lieve. So my name is Jason Finkelstein. I guess you can call me the lead developer of the web application here. It was very much a group effort, though. So as you could probably pick up, Lieve and Robin were the technical experts. They were the ones that ran the models, derived the data. They sent that data to me. I put it on the mapper in such a way that users can access the data, understand the data, and hopefully use the data in such a way that would help answer any compound flood relating questions. So hopefully the URL is shared in the chat. This is a USGS webpage, though, so very similar to any other USGS mapper that we've published. All of our mappers, this one in particular, is built using ArcGIS Online. For those that maybe are not familiar with ArcGIS Online, that's not a problem. You don't need any account access to utilize the mapper, but it's just the backbone of the application. And we use ArcGIS Online because they're very good at supporting and hosting the data and the maps without us needing to have to worry about maintaining back-end code, updating new versions of code as it rolls out. ArcGIS Online does all that for us. So that's why there's such a great avenue for us to utilize with these online mappers. So this is the main landing page that we get when you go to the URL, just background information, some disclaimers of use of the data. We can click this button down here to launch the interactive mapper. Now, this particular page is a little atypical of what you'd expect a mapping application to be. Usually you're used to one big map page and maybe some sidebar text, and all of our additional maps as we go to them will be presented in that fashion. However, I thought it was important for us to be able to view all the different hazards in one screen. So as we have all the 4 different map panels here, one for the actual compounding score, one for coastal, one for rainfall, and one for groundwater, it's nice to be able to see it all in one shot. I wouldn't recommend using this page for your analysis or doing anything overly complicated. My vision for this particular landing page would be to use the search function. And now the search function will act as a geolocation search. You could search by address, you could search by latitude, longitude, or you could simply start typing in a city, and I'll choose Port Jefferson, New York, because I think it is a very interesting case as it relates to compound flooding. The map panels will zoom there to Port Jefferson. You can click on any grid cell, and as you can see, all of the maps are now zoomed in on Port Jefferson. The same grid cell is highlighted in all 4 panels. And once we click on it, we get some data or text that pops up on the right-hand panel. The interesting case about Port Jefferson is that all the individual hazards, coastal, rainfall, and groundwater, rank quite high, 4s and a 5. In spite of that, the actual compounding score is a 1, which means although all individual hazards could happen at a quite frequently or quite severely, the actual co-occurrence is quite low. So all the individual drivers may happen, but separate from one another. This differs from a place like Bridgeport, Connecticut, where we could zoom into Bridgeport now and zoom into Bridgeport, and you could see how Bridgeport, the individual scores may not be as high as what we just saw, but the actual compounding score is a 5 out of 5. So it's very location specific. It's very dependent on the data that Robin had calculated. So as far as vision and what else you could do on this initial launch screen, I think it's good for a cursory overview of your particular area of interest. It introduces you to the scoring. You could see all the scoring in one window here. But for the actual analysis and diving deeper into the data, I'd recommend going to our larger map panels, which we will do right now. So you could use these buttons here at the top of each map panel as a way to launch the larger screen, or we have a navigation menu in the top right-hand corner. The caveat to the navigation menu is that you need to actually physically hit the down arrow. That's the only way that the options will be shown on your screen. So it's not a button per se. You have to actually physically click the down arrow, and maybe that's one of the drawbacks to using ArcGIS Online. We are within the ArcGIS Online sandbox, so we only have their tools to use, and for whatever reason, their functionality of a navigation menu doesn't allow you to click outside of the button as a whole. You have to utilize the down arrow. So there's a little ins and outs that you'll pick up as you use the mapper. We will go to the compound flood hazard map panel now, and this is probably a more typical online mapper interface that everyone would be used to. Large map panel, some sidebar text, which you could collapse if you want a full screen view. But I like the sidebar text. I like the explanation tucked in here. You could expand, you could collapse that as well. So we do allow the functionality to view the mapper as a full screen, but if you want your data layers and explanation options shown, you have that option too on the screen. Before I start diving into the data, I do want to talk about buttons and general use of the application. Think of this as our button taskbar at the top of the screen here. We have a glossary, which this is a little bit of a cheat sheet, if you would think of it that way. If you have a question or are confused about any kind of data set that we present on the mapper as a whole, the glossary should at least introduce it and explain it to you in a very simple terms. You may need to go into the actual reported data or the metadata to find what you're looking for, but more times than not, the glossary will do a good job of probably answering a lot of the simpler questions you may have about a particular data set. And it covers everything in alphabetical order, all the different data sets presented on the mapper. We have a pop-out data layers and a pop-out explanation. And I designed this so that users that have multiple screens at their workstation can have a big map panel screen, and then you could put your explanation and data layers options and windows on your second screen. Me personally, I work off one screen solely, so I do benefit from it being tucked in like this. There's an add data functionality, which I'm going to get to at the end. I'm going to do a little demonstration of adding data to the mapper, both a shapefile that you can, upload your own shapefiles to, or accessing ArcGIS Online's catalog of publicly available data. The last two buttons here is a contact us button. That's the I information button here. You could reach out to and email this URL here that I'm highlighting. It'll go to me. It'll go to a few others in the New York Water Science Center. If it's map related or map functionality related, I'll be able to answer. If it's more content related, I'll probably direct that email to Robin or Leave. And lastly, each of the pages will have an access data and download button. These will be useful if you want to actually access the mapping publications or the publications that publish the data. So, for instance, this is Robin's journal article on compound flooding, her associated data release. If you wanted to download the data directly for offline use in your own ARC Online environments, or ARC Pro environments, you could access the data and download it there directly. And each of the mapping panels will have the specified data and publication. Okay, so that kind of settles general use and buttons that you see on the screen here. Let's talk about some of the data here. So as far as compound flood scoring goes, you'll notice that we have a color flood from light purple to dark purple. If you click the explanation, you can see the color bar, the color and the associated score right next to it. You'll notice that there is not a compound flood score assessed everywhere across the study area, which is the dotted hashed line that you see on the map. Now, one important note here is that a compound flood score is only calculated when all of the three individual drivers are present. So if a coastal score is not assessed, which you'll see that the inland areas, both in, as you move further off the coast in Connecticut and inland Long Island, there wouldn't really be a flood hazard score from like coastal action. They're not going to have a compound flood score because the coastal element is not really a factor. So just something to keep in mind, that a compound flood score does need all three factors present. The other thing I want to mention is the grid cell sizing. It is a bit coarse. It's 900-meter grid cell spacing, which for a cursory overview of analyzing compound flooding is very useful. There's not really another mapper that does a three-factor compound scoring like this. So there are ambitions to improve the cell and make it a finer resolution in the future. So this is the beauty of having a living, breathing map like this. There will be updates applied. If there is an update applied, I'll do a splash screen indicating what changed and why. So all users accessing the map will be privy to if an update has occurred or not. Okay, so actual data layers on this initial compound flood mapper would be the actual compound flood scoring. You can click on any cell and get that same kind of pop-up that we looked at on the initial screen, where it gives you the individual flood scores for the individual hazards, and then your compound overall flood score. And you could have the pop-out be on the side of the screen. It could be just right, adjacent to what cell you're clicking on. So you do have some flexibility on how exactly you want to view the data. You could check the data layers on and off by clicking the check mark here. It will flip through the different flood hazards. So coastal in green, rainfall in red, and groundwater will be in blue. As you click a layer on and off, the explanation tab will update depending on what is shown. So if you're looking for an explanation or a legend for a data layer that's not shown on the mapper, it won't display on the explanation panel here. It'll only display once it's shown on the map. Lastly, on this mapper, we have the triad data that was used to calculate the different return shift periods for precip and storm surge. Robin was alluding to this in her talk. We provide that data just for background information. And I believe these data are what directly went into computing the compound scoring in that particular region. Okay, so from here, we're going to now navigate to the coastal flood hazard mapper. You can click the down arrow and navigate towards the coastal flood mapper. It's going to have the same look and feel to what we just were looking at. This is going to be the same look and feel moving forward now, where it's one large map panel and text bar on the side and explanation on the bottom left-hand corner with the ability for pop-out explanation and data layers. The nice thing about the mapper here is that we provide the actual scoring information such that when you click on a 900-meter cell, the scoring of that cell is shown for all the hazards. But since we're on the coastal flood hazard map now, we get a little bit of more information as to the scoring and what went into the scoring of this particular grid cell. We also provide the ancillary data that went into the compound or into the actual scoring for the particular hazard. So for coastal flood hazard score, a wave score was assessed, an inundation score was assessed, and the actual inundation extents that went into the inundation score are provided. Now, you'd have to kind of refer to the coastal flood report to figure out and look up how the scoring was actually derived using these inputs. You'd have to refer to Salme, Cook, and Leave Hardman's report, and you can access it via the URL provided in the Access Data and Download dialog box. But for here, I think it's important to note that not all of our data is provided at just the 900-meter grid cell spacing. We do provide high-resolution data, and we have like one or two high-resolution data sets for each of the maps. So what would be interesting to look at here is the annual exceedance probability for the different return periods, the 1 year, the 10-year, the 25-year, and 100-year. Again, we could pull up the explanation and see the different colors that represent the different return periods. So I think to really view this, it would be best to dive into a particular area. So I'm going to go back to Port Jefferson. It zooms us into Port Jefferson. There may or may not be some latency lag as you load the data. I'm not really surprised by this at all. The rasters are quite large that are feeding, or that are fed into the mapper here. And with multiple people accessing it at the same time, I'm not super surprised that the latency here takes a little bit longer to actually draw this at a super high resolution. So I kind of anticipated this to happen. So I'm going to pivot real quick to a PowerPoint here that I have of screenshots of what I wanted to show as it relates to the inundation extents here. So hopefully everyone could see my screen. Kathleen, can you tell me if you could still see the PowerPoint here?
Yeah, you're good.
Great, thank you.
It's in that other the notes view. If you want to just go to display settings and hit swap up at the top.
How about I just do that? Or display settings and hit swap. How's that?
Perfect. Thank you.
Thank you. So you can see now that we're at a finer resolution here. It's down to 1 meter grid cell spacing based on the 1 meter LiDAR that this was derived from. As I click through here, we can click the explanation and see the different colors as they relate to the different interval periods. So obviously your 100-year storm is going to be further inland than your 1 year storm. So the lighter shades will be shown closer to the coastline, whereas your darker shades will be shown further inland. I think we could probably view this in a somewhat better fashion. So we have a base map button here, and I think it's a good idea to click the base map button and then switch our base map to aerial imagery. That way we can kind of see what things look like from a aerial imagery view. We could actually increase the transparency of each individual layer. So we could increase the transparency on that. I boosted it up to above 50%. And you could see now that the inundation extent is now overlain with the aerial imagery. And we also have a future conditions inundation where it assumes a sea level rise of a 0.5 meter. And you could really investigate and play with all the data here, visualizing it all on the same screen, where you have your current conditions, inundation versus your 0.5 meter rise in sea level. And there's a little bit of hydrodynamics that go into this. So the 0.5 meter rise goes a little bit further inland than just a 0.5 meter rise in the LiDAR. I'm going to go back to my online mapper here. I'm going to fly through the other windows here. So now I'm going to go to the rainfall extent, the rainfall mapper here. Again, same kind of look and feel. You can click on any one grid cell and it gives you the scoring metric that went into the rainfall. All the hazards are shown here. And this little blurb of text will be directly correlated to rainfall. Like the coastal information, we do have high resolution data for rainfall. We have a ponding layer, which Leave had alluded to. So we could zoom in and maybe this will load, maybe it won't. But I'll revert back to that PowerPoint real quick. And we could look and see that let me display this and go back to that. We can see that this is high resolution ponding data, and this would be indicative of closed depressions that when precip occurs, these are the areas where we'd expect water to pool up where there's not too much of an escape. Now, this doesn't really factor in any kind of sewage drainage system, so that's a caveat to this. You'd have to find those kinds of caveats out by looking up the actual metadata to these layers, and you could access that metadata via the access data and download dialog box where you can click on the report, and the link to the actual data release is there. And again, all ancillary data that went into making the score is going to be shown on the mapper here. So you can click on and off the different layers. Stormwater runoff, I know Leave had mentioned that. This is a higher resolution data set too. It's not just that 900 meter grid cell spacing, the slope, and different precipitation totals. And again, as you click on and off the different layers, the symbology is shown in the explanation tab. I will now move forward to the groundwater emergence map panel. And again, we could do the same kind of thing. We're going to click on any particular grid cell, and we could analyze and look at the different score. So if groundwater is a 5 out of 5 here, and you can see how it relates to all the other hazards and the overall compound score. Again, you'd have to refer to the actual report and data release to get the calculation of how the score was derived, but we provide all that ancillary data. So depth to water table, and this is high resolution again. So you can imagine that where you have depth to water very shallow, and the shallow scores are going to be where it's red. If you go back to your explanation tab, it'll be a depth to water with a color flood from red to blue, red being the most shallow, closest to land surface, blue being much deeper to the water table. And you can click on any grid cell here, and it will give you a derived value based on the interpolation that was performed by the study. And you can see it varies quite dramatically in some places. even, so closely together, you can get quite dramatic differences. We also show hydrologic soil groups. Now this is back at your 900-meter grid cell spacing. So some data sets we present at much finer resolutions, and other data sets we show at that 900-meter spacing that the overall scores are shown at. Some data sets are only shown for particular regions. So for this particular data set, the depth to water with an assumed sea level rise, it's an alternate scenario. It's a 6 feet sea level rise, and we give an alternate view to what the depth to water may be in that scenario. Now, why is it only present for Long Island? It's not a loading glitch by any means. It just so happens that the groundwater model that went into the development of this particular data set for Long Island, they had a sea level rise scenario built into that groundwater model. New York City and Connecticut does not have that as a built-in scenario to their groundwater model that we like took from. So we don't present it in that area because it's not available to us even. I think that's kind of everything that I wanted to cover. The one thing, actually, before I pass it back off to Kathleen, I did want to go back and mention the utilization of adding data to the mapper. So I've had questions of, can users do spatial analysis within this interface online? The answer to that's going to be no, because all the data that you're doing isn't getting saved all the meanwhile. It's good for the particular instance that you're looking at the mapper, but if you wanted to have something that you refer back to at a later point in time, you would be best served to download the data from ScienceBase or data repositories and start your own online map and kind of build upon that with all your data sets. But again, you could add data to the mapper for a single use, and you could add data via a shapefile or file geodatabase. So I clicked on add data. I'm navigated to the particular Windows directory that my shapefile is in. It's a .zip file. It needs to be a .zip file, so you have to take all your shapefile components. There's usually 6 or 7 or 8 components that you have to zip up as one singular file. You could add that into the mapping interface here. You have to click OK, click Done, and then you have to, it's not in the mapper yet. You actually have to click this Actions button and indicate that you want to add it to the mapper. So now my study area demo shapefile is in the mapper. When you add a shapefile to the mapper, all of your attribute table information will also be available to you when you click on a particular shape. For this purpose, for this demonstration, I just made a simple shapefile here of different study areas across the landscape here. I did one for Bridgeport, Montauk, and there's a little shapefile here indicative of Port Jefferson. So that's how you would add data via shapefile. The last thing I want to do is adding data through ArcGIS Online's online database. So both ArcGIS Online and state, county, township, municipalities often do have a GIS library of their own that you could feed. You could actually use their data and bring it into this map. So for this particular exercise, I'm using just a USA wetlands map data layer here. And I'm going to click this, and I'm going to get this error message here. Please sign into ArcGIS Online. So not all of the data that is built into this you could utilize without being signed in. So at that point, you could sign in using your username and password to ArcGIS Online, or oftentimes than not, there'll be a secondary free version, not free, but public accessible version that you don't need a login information for. So I clicked that second version of USA Wetlands. I'm going to add that to the mapper. It's going to zoom me way out because it's a USA Wetlands data set, but we'll zoom back into our area of interest. And we're going to shut off some of the other layers here. And you can see now that the USA wetlands data set is added to the mapper, where you'd expect to see wetlands. That's going to be where, where they're shown. You can click on any one of those uh, shapes and get the background information as it pertains to how the DEC wanted this, or the wetlands data set published by Esri wanted it to be um, attributed here. So a bunch of background information. You're subject to whatever data set you're bringing in. So however the author of that data set wants you to view it, that's what you're going to end up seeing. And yet you could use other agencies' data, bring it into this mapper here. So this isn't a one-stop shop by any means. We want this to be a different tool in the, a different mapping tool application to be used with everyone else's, flooding map applications that are already out there. And with that, Kathleen, I'm going to pass it back to you.
Perfect timing. Thank you, Jason. And yes, thank you everybody for sticking with us. Again, I want to, acknowledge that this is a lot of information, and we went through it pretty fast. So, I'm gonna just slideshow this one more time. If you have any questions, feel free to reach out to myself, Leave, Robin. They have more information on the content. And if you have any technical questions, please reach out to Jason. They are happy to answer any questions, concerns, help with anything. Again, the QR code where we will be collecting any of your feedback, thoughts, questions, comments. And again, we will be circulating. This was recorded. We'll be circulating the recording, which will most likely live on the Long Island Sound Resilience Hub. And we'll be circulating that, as well as all the document where we compile all of the answers for the questions that we collect after today. So those questions will be answered, your comments will be heard, and we will follow up. And I just want to once again thank USGS for coming today and presenting all of this great work, and taking the time to share it with our users. And we are looking forward to hearing more from everybody. So with that, I will wrap up here, and thank you again for your time.